Okay, so one way to look at it is as follows. So for example, we are trying to find an antiderivative of something like this. So I wrote 1 plus x squared. Okay, so just playing with the algebra. So we also have dx here. So we look at these things. What does it look like? So for example, if you have d of the function x squared, this is 2x dx. And we have this x dx part here. Okay, so from here we can say that 1 over 2 dx squared is x dx. So we substitute that here. Okay, so instead of this I'm writing this 1 over 2, but 1 over 2 is a constant. In integration it comes out 1 plus x squared dx squared. Okay, so this part is used here. Okay, just playing with algebraic equations, we notice here that if I take differential of the function 1 plus x squared, I will have 2, well, okay, without, without actually finishing it, differential is additive. Okay, so this is differential of 1, which is 0, plus differential of x squared. So this is differential of x squared. Okay, so differential of a constant is 0. Okay, so instead of dx squared, I can also write this. So this part is used here. I have 1 over 2 integral 1 plus x squared d 1 plus x squared. Okay, so I treat 1 plus x squared as a block. Okay, since I'm treating it as a block, I give a name to that block. So let us say at this point, I consider this thing as u. So every time I see that, since I'm algebraically looking at it as one entity, so this is 1 over 2 square root, integral of square root u du. Okay, now suddenly life is easier because now I know which function will give me square root u if I take its derivative. Okay, so from here, let's go here. So this is, if I take u to the power, okay, so I try it like this. If I take u to the power 3 over 2, if I take its derivative, okay, so if I take its derivative, I'll have 3 over 2 u 1 over 2. Okay, so I'll get this thing, but I don't have 3 there, so I want to divide this thing by 3. Okay, so if I divide this by 3, I'll have exactly this one here. Okay, so this is what I have here. Okay, so this is the antiderivative plus c. Okay, now one is tempted to stop here because suddenly we got rid of the integration sign, but we try to remember what we started with. We started with this thing. We wanted to find a function whose derivative is equal to this. Well, this is not a function whose derivative is equal to this, algebraically speaking, because it's a function in u, this is a function in x. So we do the substitution here again. Okay, so we take the substitution, put it back here. So this is 1 over 3, 1 plus x squared, 3 over 2, plus a constant. Okay, so now this is the function. This is the answer to our problem. Okay, so this one and this one. Okay, so what I did in between is actually a formal discussion. Okay, but we can also make it theoretically sound by playing some games. So why did it work? Okay, so this is, you see, integration is inverse of differentiation. If I take the derivative of this, I'll obtain this. So how do I understand the in intermediate steps? So I start with two things. Suppose, so first here I used this simple thing, okay? So the derivative of this is equal to this. So I know an antiderivative of this, but u is a function composed of these things. Okay, so I try to find a theoretical basis for this. So first, let me imitate that. Let f be such that f prime is equal to f, small f. Okay, so we are here now. Then chain rule says if I have f composite g and I take its derivative at x, okay, so chain rule here, g is this part here, okay, so maybe I just remind ourselves what we are doing. So this g part is this part, and f is this square root u stuff. Okay, so now chain rule tells us how to take the derivative of this. This is f prime at g of x times g prime of x. Okay, now going back, I know what f prime is. Okay, so this is f of g of x, g prime of x. Okay, so what we want to do is, suppose I want to add a differential to this. Okay, so f composite g x prime dx is equal to f of gx g prime x dx. Okay, so this thing is, all of this is differential of f composite g of x. Okay. And you see, now this is what we are trying to do. This is why this thing works. We looked at this function. Okay, so we looked at this function, and we wanted to see it like this. Okay. Now, then, knowing an antiderivative, since I already see this as the derivative of something, I have g in mind. The only thing that remains is to find an antiderivative of f. So all that remains is to find an antiderivative of this simple function. Okay? So once I find them, I'd compose f and g, small f and g, and that's the antiderivative of this. Because if you take the integral of this, you just get integral and differentiation are opposite things to each other. Okay? So remember that d f composite g of x is equal to f composite g x. Okay, I'll take integrals of all sides here. So I'm interested in the integral of this. It will immediately give me what I have here. Okay, so this is why it works. It's nice to keep these things in mind, to know that what you are doing is correct. But you actually, once you have a theoretical background, you go back to the problems and you play with them, because you see, looking at the function, this is the function I am looking at. Looking at a function, there is no method of seeing it as f composite g. Okay, so that's the bottleneck of this technique. Okay, that's why most of the time we consider integration as an art. Okay, so there's no method for this. You have to look at it. You must have done lots of examples so that you know what to try first. Okay, so you try several things. Sometimes it works, sometimes it doesn't. That's integration. Okay. So the whole problem here we'll solve now lots of problems. The main problem in these things is to look at a function. So this is my function, that red function here. Okay, to look at this function and see it as this. Okay, so this technique will work if you can look at integral h of x dx and see it as h of x equals f of g composite x g prime x, and find f such that f prime is equal to small f. Okay? Then integral of h of x dx is equal to integral of f of g of x g prime x dx, and that's equal to f composite g of x. Okay? Because I find an antiderivative of this, and this one I already see it as the derivative of something, so g is available. Okay, so you see that this looks like a miracle. Okay, so you look at this, and suddenly you see something else. Okay, so the only way it works is because you have solved lots of examples, and you know that sometimes this works. It works much easier than it sounds. Okay, so let us do some examples. For example, I'll start with this one. Let's start with easy things. X cubed cosine x to the 4 plus 2 dx. Okay, so most of the problems we can solve are of this form. Of course, this is not the only kind of problem we face, but there are lots of cases where these things happen. So you know an antiderivative of cosine x. Okay, so so this part, for us, this part is easy. And then this function is composed with this, and its derivative appears here, up to a constant. Okay, so constants are not that important because you can multiply and divide by the same constant. It will not change anything. Okay, so then if cosine is my small f, inside is my g of x, I take the derivative of this and I check if g prime is here. Okay, that's here. Okay, so this works. Now, instead of going through all these intermediate steps, we immediately start with this step. Okay, so here you say put u equals x4 plus 2. Okay. Now I can substitute this, but I have to substitute this also. Okay, so that's the reason why in defining integrals from the beginning we put dx there. There was no reason to write dx there, okay, because we fooled ourselves by saying that we'll put dx there so that it reminds us that we are integrating with respect to x, okay, but that was a lie. Now we correct it. Okay, the only reason why we have here is because this chain rule stuff works with integration, and actually we are integrating d of something. Okay, so there is d of something. All of this is inside here. When you take the differential and simplify, you get this. Okay, and the antiderivative of this is what you see inside. You take everything inside d. What you see here is the antiderivative. Okay, so that's how the actual mechanism works. So we are trying to recover that. Okay, so that's the reason why I want to find dx. So you take dx, d of both sides. So you have du is equal to 4x cubed dx. Okay, so you don't have 4 here, but as I said, 4 is easy in integration. So if you want, you can go one more step here. You have 1 over 4 du equals x cubed dx. Okay, now I have x cubed dx. I will replace it by this. Cosine of this will be cosine of u. Okay, so now I put this here. 1 over 4 integral cosine of u du. Okay, so you see I immediately came to this step. Okay, so in between, I summarized how I played algebraically with those symbols. So everything boils down to this. Okay, now I know an antiderivative for this. I have 1 over 4 here. And antiderivative for cosine u is sine u. Okay, so if you take the derivative of this, you will get 1 over 4 cosine u. Okay, so final step is, since we are trying to find a function of x whose derivative is this, I want to write a function of x whose derivative is that. So you put this substitution back in, you get 1 over 4 sine x to the 4 plus 2 plus c. Okay, so we found an antiderivative. Okay, so sometimes life is easier. We have 2x plus 1 dx. Okay, so again, I know how to find an antiderivative of square root, but square root is composed with the function here. So we try to play on that composition. We put this thing as u equals 2x plus 1. du is equal to 2 dx. Okay, I don't have 2 dx. 1 over 2 du is dx. Okay, so 1 over 2 square root of u du. Okay, so dx is substituted by this. And what I see inside the square root function is this is my g of x is here. Okay, so I know an antiderivative for this. So this is what 1 over 3, let's check, u 3 over 2. If I take the derivative of this, I get square root u, okay, plus c. And I put this substitution back, 1 over 3, 2x plus 1, 3 over 2 plus c. Okay. Now here this worked because after I differentiated this, I get something here. If I had x squared here, you see it would not work in this case. Note, if we had integral square root x squared plus 1 dx, okay, and we put u equals x squared plus 1, du is x 2x dx. Okay, I can get rid of this 2 by pushing it to this side, 1 over 2 du equals x dx, but I have this extra x here, and it's not showing up here. Okay, so with this integral, this method will not work. Okay, so that's that's why in the examples we carefully choose the antiderivative for which this method works. Okay, so for this one, we will use trigonometric substitutions, and most of the time these are very commonly occurring integrals. You just look them up in a table. Okay, so in order to make this thing work, I must have x here. Okay, if the problem is x times this, then it's precisely a case of substitution, because the derivative of inside function will be here if you have x here. If you don't have x there, then this method will not work. So you will have to try other methods, which we will come step by step. Okay, so try another method. Okay, so we'll find this later. Okay, so that shows us that if we are trying to cook up a problem, we have to, in our mind, we have to compose a nice function with a complicated looking function, but of course it shouldn't be very complicated. Then you take its derivative and multiply it out. So that's a nice problem for integration by substitution. So let's try an example here. So this is what I did. Integral x square root of 1 minus, okay, so for some reason I had 4 here. for x squared dx. Okay, so by experience, you immediately check that the inside of the square function is a polynomial whose derivative appears there up to a constant. Okay, again, while you are trying these things, you don't be precise at first. You have to be precise when you start writing it down. Now we are checking if the method of substitution will work. I know how to take the derivative of antiderivative of square root, whether it is here or here, because it's just of the form u to the power something, minus 1 over 2 plus 1 over 2. I can find its antiderivative easily. It is composed with a function whose derivative appears here. Okay, so the derivative of this basically is x. Okay, and it is here. So substitution must work here. Okay, so we try substitution here. Let u be 1 minus 4x squared. Then, since I'm also trying to substitute this, in this substitution, I must recover dx. The only way to recover dx is to take differential of both sides. I get minus 8x dx. So fortunately, I have this thing here. X dx is there. Okay, so minus 1 over 8 du will substitute x dx. So this thing is going to be minus 1 over 8 integral. This is going to be du because I put the minus 1 over 8 here. And this thing is square root u in the denominator. So u to the power minus 1 over 2 du. Okay, so the whole idea of substitution is to bring it down to a form where you recognize it. Okay, after this point, we have to know what to do with this. So this is now, here we are using let me remind you what we are doing here. This is u to the power n du is 1 over n plus 1 u m plus 1 plus c when n is different than minus 1. Otherwise, we'll get logarithm, and we'll do that later. Okay, so we play with this, minus 1 over 8, 1 over minus 1 over 2 plus 1, u to the power minus 1 over 2 plus 1 plus c. Okay, so I did this, well, I didn't do it here, so let's do it here. So this is 1, 2, 4 minus 1 over 4, right? And then this is u to the power, well, instead of u, I'll put 1 minus 4x squared. And this is 1 over 2, right? 1 over 2, well, that's what you get. You take the square derivative of square root, you get 1 over square root plus c. Okay, correct the calculations? No? Okay. So now this is an antiderivative for this function. Okay. So let me see if I have, I'll do this and okay, so I will come to this slowly. Okay, so let's start with, again, something easy. We have cosine 5x dx. So what substitution do you suggest here?
5x is equal to u.
Huh?
5x is equal to
5x, okay, so u equals 5x, so that will work. Du is 5 dx, okay, so I just don't have 5 here, so dx is equal to 1 over 5 du dx, 1 over 5 cosine u du. Okay, so now I have 1 over 5 sine u plus c, 1 over 5 sine 5x plus c. Okay, in this, Well, actually, after you get used to this, in these simple problems, you do this mentally without doing any substitution. Since you don't have any squares or other things here, derivative of sine is cosine, so the answer will be sine x, but derivative of sine x will give you cosine x, not 5x. So put sine 5x, derivative of sine 5x will give you cosine 5x times 5. Well, okay, if the only thing that's differing is constant, you divide or multiply accordingly, and you do this immediately in your mind. Also, here you could have done the following. Let u equals cosine 5x. Why not? Will it work? Okay, then let's say cosine sine phi x, u equals sine phi x. Okay, because you are suspecting that the answer will be something with sine. Okay, in this simple example, it's trivial, but even in more complicated problems, sometimes this works. You immediately guess something more or less about the answer. You try it here. So you see du is equal to 5 cosine 5x dx. So you already have your problem. So this only comes to this side, and you are here. You immediately write this. Okay, so this integration is just a game. Okay, so let's step up a little bit. So I'll have integral x to the 5 square root 1 plus x squared dx. Okay, any idea for substitution? Well, first step looks obvious. Obvious doesn't mean that it is the step that will solve the problem, but here, if you can't think of anything else, the only thing that's bothering you is the square root sign there. If you didn't have that square root sign, x to the 5 would be nice. X to the 5 times 1 plus x squared would be nice. You can integrate those things easily because they are polynomials. So in such things, life experience tells us that you substitute either u equals all of square root 1 plus x squared or just what you have inside 1 plus x squared. One of them, both of them will lead you somewhere. Okay, so either you like where you are or not, then you go back. If you don't like where you are, you go back and try the other way. Okay, so first of all, maybe we can try 1 plus x squared as u, because square root function is again a sort of polynomial. It is something to the power 1 over 2. We know how to integrate something to the power 1 over 2. So let us make that something 1 plus x squared. And let's see if we can handle x to the 5 later. Okay? We don't want to solve all of them at once. Okay? So in integration, you always say, I'm now trying here, try u equals 1 plus x squared. Okay, so if you ask, how did you find u equals 1 plus x squared? Well, I just picked it up. I'll try it. If it works, it works. If it doesn't, I'll erase all of it, try something else. Okay, so du is equal to 2x dx. Okay, I have x dx here, and I have lots of other things. So, but let's do it step by step. I have x dx. So what is left is here x to the 4. Okay, one of these x combined with dx will give me the new du. Okay, so what do I do with x to the 4? So x to the 4. What do I do with this? How do I replace it in terms of u? So that's the, yes?
We can say u minus 2 equals to x squared. And
u minus 1 is equal to x squared, and then
will be the
and do this. Okay, let's do that. So from here, we have x squared is equal to u minus 1, as your friend said. So x to the 4 is equal to u minus 1 squared. Okay, so it looks like we have changed everything to u, and now we put it in and hope that we can understand the new integral better than this one. Okay, so now x dx part will give me 1 over 2 times du. And here I have u minus 1 square. And here I have u to the power 1 over 2 du. Okay? Okay, now let's play with this. So this is u squared. So let me do it in two steps. U squared minus 2u plus 1, u to the power 1 over 2 du. So this is 1 over 2 integral u. 2 plus 1 is what? 5 over 2 minus 2u 3 over 2 plus u 1 over 2 du. Okay, so this is equal to 1 over 2. Now I can integrate these things, right? So first I write this like this so that later I'll check if I did these things correctly. If you trust yourself, you can do this mentally immediately. 2 over 3 over 2 plus 1, u 3 over 2 plus 1 plus 1 over 2 plus 1, u 1 over 2 plus 1 plus a constant. Okay, now let's substitute 1 plus x squared for these things. Okay, so what is this number multiplied? So this is 7 over 2. 2's will cancel, 1 over 7. Okay, 1 over 7. And this thing is u is 1 plus x squared, and this is 7 over 2. Minus. Okay, so this 2 cancels with this. I have 2 over 5. Okay, agree? It's your responsibility to scream if I write something wrong. So this is 1 plus x squared, 5 over 2. Plus, this is 2 cancels, so 1 over 3, u 3 over 2. Instead of u, I want to write something else. 1 plus x squared, 3 over 2 plus c. Okay? So this tells us how to handle things like this. When you have extra, if I had only x here, that would be easy, okay, baby stuff. Now we are growing a little bit, so we put here more than what we need. So we are hoping that the extra stuff can still be expressed in terms of u. So that worked. So this method worked here. Sometimes it doesn't, okay. If it doesn't work, then you try something else. In integration, there is no rule. There are lots of techniques. It's just like playing chess, okay? You learn the rules of integration. You learn techniques of integration, just like you learn certain techniques and strategies in chess. Then none of these guarantee that you will win a game. You win the game yourself. So it's the same in integration as opposed to differentiation, where once you learn the rules of differentiation, you differentiate almost everything. When I say almost, I'm saying that sometimes some piecewise functions are defined. Okay, it takes some work. Rules don't apply there. You have to use definition. But whenever you have the rules and the function obeys the rules, you differentiate, but not in integration. Okay, so I have all this complicated stuff here. So before that, let me try something like this. Okay, let's say sine cube x times cosine. Okay, let's first do this, dx. Okay, so what do you see when you look at this immediately as far as substitution is concerned? Okay, so this part is d of sine x. Okay? So I can do this like this if you feel like you are good at calculus. Okay? So something cubed d something is equal to what? 1 over 4 something to the power 4 plus constant. And the only nice thing about integration is you definitely know if your answer is correct or not. Okay? Take the derivative of this. If you get that, the answer is correct. Okay? It doesn't matter what you did in between. So this is one way. Or you can do this thing formally. You say I'm putting u equals cosine x, then du is going to be sine x dx, and I substitute these things now. No, I want to do it the other way around. U equals sine x. Okay, this is what I did here. U equals sine x. Du is cosine x dx. Okay, now I can express everything in terms of u. This is u cubed. And cosine x dx just appeared here, du. And I have 1 over 4 u to the power 4 plus c. And then this thing is equal to this one. Okay, let's complicate this a little bit. Integral sine cube x cosine square x dx. Okay, so I just pumped it up with an extra cosine. So what do you suggest now? Shall we try the same thing? So that's the general philosophy in life. If something works, you try it again until you fail. Okay, then you find something else. If you put u equals sine x, what will happen? Okay, so try u equals sine x. It worked here. Okay, du is cosine x dx. Okay, so we have cosine x dx here in terms of u. I have sine cube x in terms of u, but I have an extra cosine there. Okay, so let's try. So this thing, so sine cube, I'm working here. Sine cube x is going to be u cube, and cosine square x dx is going to be cosine x times cosine x dx. And this part is du. I have cosine x du. But I also want to write this in terms of u. So cosine x is square root 1 minus sine square u. Square root 1 minus u square. Or first let me write sine square, because later on when I come back, I want to know what I did so that I check if it was correct or not. This is sine square x du. So now I can write this in terms of u. 1 minus u square du. Okay, so I wrote everything in terms of u. Let's check what happened now. Sine cube is u cube. And this stuff is 1 minus u square du. Okay, so it's not very beautiful. You keep this in mind because we know you can handle this. We had something like this here. You see now I can do one more substitution here. Okay, just like that one. You see this is almost like that one because I take the derivative of inside, I'll get one of these u, then I have u squared, but I'll do it as I solved there. Okay, let's do that. Okay, invent a new name, w. Let w here equal 1 minus u squared. dw is equal to minus 2u du. Okay, I have these things here. So this is minus 1 over 2 dw is equal to u du. Now I can substitute everything in terms of w. So I have minus 1 over 2 integral. Here one of these u's will match with this one. I have u square, and u square from here is 1 minus w. Okay? So I have 1 minus w, and 1 minus u square is w to the power 1 over 2 dw. Okay, so this is easy. I will not do this because I'll show you an easier way. We have time for this. So this is w 1 over 2 minus w 3 over 2 dw. Okay, so now it's easy. Okay, so we managed to do this, but let's try something else. Now we go back to this. Now we are psychologically free. We know that the problem can be solved. Can we do it in an easier way? Okay, so trying u equals sine x wasn't nice, so maybe if I try something else. What do you want to do in this case? If I take okay, so if you take one of those sine there and then try. Okay, so if I take sine x dx as d cosine x, okay, I have cosine here, I have sine square here. Sine square can be written in terms of cosine, so I'll have an easier expression in u. Okay, so let's try that one. Okay, so another try, approach. So what was the problem? Sine cube x cosine square x dx. So let me say u equals cosine x. See what happens. Du is equal to minus sine x dx. Okay. Okay, so minus du is sine x dx. Then here I will have, so I'm taking this sine u and I'm writing it sine x times sine square x. So it's going to be equal to sine x 1 minus cosine square x. This sine x together with dx will give me du. Okay, so I have this minus sign here, minus. So I wrote this thing as 1 minus cosine square. Cosine is u, 1 minus u square. I have u square here and du. You see that suddenly I have something easier. Okay, so this is u square minus u to the 4 du. I have minus. So let's put this minus inside. Okay, so u for u square. Okay, I put the minus inside. Now this is 1 over 5 u 5 minus 1 over 3 u cube plus c, and that's equal to 1 over 5 cosine to the cosine 5x minus 1 over 3 cosine 3x plus c. Now here, if you put all these substitutions back, you will, for w, you will put 1 minus u square, and for u, you will put sine. So actually what we did is we put u equals cosine square there. Okay, you simplify this, you'll get a trigonometric expression which doesn't look like that one. Okay, but they should be the same. When you try trigonometric identities to simplify that one or this one into that, you will see that they'll differ by an additive constant. Okay, but an additive constant is integration constant. Since you will have lots of sine square, cosine square, when you add them, there will be one or two, some constants coming. You will have a constant. if you simplify this thing, you will have that function plus c plus some other number you find, 1 or 2. Okay? So since that plus c means an arbitrary constant, you put all those constants together, and the two expressions will be the same. So that's why we insist that you write the plus c there, so that two different equations, two different expressions for the antiderivative will be the same after you play with the constants. Okay, let's look at something else. We have, talking about tricks, we have also a function like this. As I said, you cannot always integrate something, so I don't know what the number was, 6, 7, 8. So this time let us be ambitious and let us try to find this thing, tangent x cubed over 2 plus x squared plus 7x to the 4 dx. Okay, so nothing will work here. Okay, so there's nothing to substitute. You immediately see in your mind, yes? Huh? It's 0, yes, that's what we are coming to. Sometimes before you blindly start applying one technique after another until you get tired, you have to step back and check what the function is doing. Okay, so this is an odd function. Okay, so whatever the graph of the function after, on the positive side, it is the same on the left-hand side except that everything is negative. Integration is calculating area with a sign. So the area under x-axis here comes with a minus sign. The same area appears on this side, so they cancel each other. Okay? So we look at this thing, call this f of x. F is an odd function. That is, the definition of odd function is the value at negative x is the same as minus 1. So maybe I make an exaggeration here. This is minus times f of x. Okay? So the graph is something like this, not in this one. I don't know what the graph of this thing looks like, but an odd function always passes through the origin. Is it correct? Because you see, if I put 0 here, whether I put minus in front of it or not doesn't matter. So this is 0. The value of the function at 0 is equal to minus 1 times the value at, again, 0. So the only value should be 0. So the function passes through the origin. So sine x is a typical example. So let me do this with sine x. So this is, for example, sine x. Okay? So the area here is the same as the area here, but integration gives this area as minus 1. Minus 1 times this area. Because in integration as height, you are taking the value of the function. Okay? The value of the function is negative here. So these two areas add up. So let's say this is a minus a. So this is y equals f of x, f odd. Now integral from minus a to a, f of x dx is 0 because of this picture. Okay, so here you don't try any technique. You just check that this function is odd. This part is even powers, and this is odd. And by the way, that's why we come with the words odd and even. A function f is even if f of minus x is equal to f of x. So this comes from generalization of polynomials. You look at this polynomial, only even powers appear. This polynomial is an even function because it swallows the sign minus 1. And it gives you, whether you put minus or plus, it gives you the same value. If instead of 2, 4 here I had 3, 5, then if all power, and I don't have this because an odd function must be 0 at 0. If I had these things, but the powers were odd, then I would call it an odd function. So that's where the words odd and even come from. And next semester when we do Taylor series, a nice function will be given as a summation of x to the power something. If all the powers appearing are even, the function will be even. Otherwise, if all the powers appearing are odd, the function will be odd. It will be a generalization of polynomials. You will have a non-stopping polynomial. If all powers are even, the function is even. Let me check if we have missed something. So I think we didn't miss anything. Okay, so I'll do this next hour. Okay, let's take a break here. I'll continue with this next hour.